Hi, welcome to the third session on what is complex analysis about. Today, before embarking upon the so-called multivalued functions, let me say something very interesting about the Cauchy integral formula which was derived at the end of last session. Okay, so let me do the screen share. So this is a very beautiful result which is not very well known. Suppose gamma is a path. Right? By gamma I denote by image of gamma. Okay, this is a subset of C, right? Okay, now suppose I have notice that this is a compact subset. These things are not needed for what I am going to say, but it will be useful. And let's look at f is a continuous function from C minus gamma to C, a continuous function, right? Then define g of z to be integral of f of w by w minus z over the path gamma. This is Cauchy-type. This is known as Cauchy-type integral. And notice that this w is going to be over gamma, therefore I have to say this z should not be in gamma, right? Okay, this is the result, a beautiful result. Let me call it a theorem. Then G is analytic on C minus gamma and hence holomorphic on okay. So in particular, okay, the proof is very easy, not very easy in the sense that suppose this is gamma, okay, and choose a z there, then you can choose an r such that b is, suppose this is your z, bz to r, okay, if you want even take it a close one, that intersected with gamma is empty, because this gamma is a compact set, you can always choose such a thing. This will be another one. Okay, then in this you can expand w minus z into geometric series. Okay, I will not go into too much of those things. So we will show that if you want make it as a or something, okay, and for every z here, okay, I can do something. My w are going to be here, okay, geometric series in BAR. Okay, so this is not so well known result, but can be found in my book. So notice that this gives us a way of generating a lot of analytic functions. What all we have to do is very simple. I just have to look for a, a, a path and then a continuous function, okay, outside that. Okay, even you can see I don't have to, this maybe even, so this has to be, I'm just to modify, see f of w I want to integrate, this is path. Okay, I'm sorry for this. F must be continuous function on the image of gamma. Okay, because that's all it matters here. I don't have to worry about what is f of w. I have to make sense of f of w only for w which lies in the image of gamma, right? Therefore I need only continuous function of f from gamma to C, right? Okay, so and this Cauchy-type integral will always give me an analytic function which is analytic outside the image of gamma. So in particular, uh, in particular, recall Cauchy integral formula. What does it say? If f is holomorphic and if BAR is contained in some open set, okay, f is holomorphic on U, right? Then it said just make it z if you don't want for every z. So f of z is given by 1 by 2 pi I or gamma of r, where gamma r is the circle. R e power 2 pi I t is less than or equal to 1. Okay, and f of w by w minus z. Okay, notice that. So now notice that f is holomorphic on all of you, therefore f is going to be holomorphic on this circle. This circle is completely contained on U, therefore this is a Cauchy-type integral by the last theorem, by the last result, right? It is a Cauchy-type integral. Therefore the resulting function f must be analytic. Are you following? Please pause review. Therefore f is analytic on BZR, and this is true for every z in U. Therefore its f is analytic on U. So pause, review, proceed. So okay, so after this digression, let me go to the so-called multivalued functions. Okay, the first thing is, okay, one has to understand the exponential series. So what did it say? It said that if I define by exponential z or simply e power z, by definition this is same as z power n by n factorial 0 to infinity. We know this is convergent for all C, and this defines a holomorphic function. Okay, right. Now this holomorphic function is such that e power zw is same as e power z into e power w. Okay, this satisfies this standard property I have seen in exponential function real analysis. In particular, if I write z equal to x plus iy, then e power z will be e power x into e power iy, and this you can see by using the formula for exponential function. This will be cos y plus I sin y. Therefore modulus of e power z is e power x. Okay, these things can be rigorously proved. Okay, and your cos and sin also is defined by means of power series functions, as you have seen in power series lectures, right? See, the so-called trigonometric function, exponential function, from calculus you learn how to use. Very rarely one learns the properties and derives the properties rigorously. Okay, and if you are a serious student of mathematics, I will suggest just go through that. Okay, in my book there is one small chapter on this. Go through it, whether it's needed for your exam or not, you learn it. Okay, you do not remember the proof, but go through it once so that you know for sure, at least I have learned all these things rigorously once in my life. Okay, that should be your aim. Okay, right. Have you understood this? Right. The most important property is the following. Okay. Let S1 denote the set of complex numbers so that mod z equal to 1. This is the so-called unit circle in C. Right. Then what we know is, okay, for any z in R, there is a real number t in R, so that z is of the form u power it. Right. And 2, if e power z equal to e power w, if and only if, okay, there exists an integer m, so that z minus w is m times 2 power I, 2 pi I. That means, notice that this means x, if I write the real part of z must be the same as the real part of w, but therefore imaginary part of z minus imaginary part of w will be some multiple. It belongs to 2 pi I times z, a multiple of 2 pi I. And hence when I come to this, okay, this t is not unique. Okay, and if I put s equal to t plus 2 pi m, then e power is will also be equal to z. It's not unique. Okay, right. The next thing is the so-called polar decomposition, polar representation of a complex number. Given z, I can write it as z. Let us look at z by mod z. This is a complex number w. What is the absolute value? It is 1. Therefore, w belongs to s1. Therefore, what do I know? I know there is a t in R, so that e power it is w. That is same as saying my z is mod z times e power it. And this t is not unique, as you know. Right? So this is called the polar representation. Right? So this is something like r e power it, therefore r cos theta, r sin theta. If I write e power it as cos t plus I sin t and break it into real and imaginary part, the ordered pair will be r cos t, r sin t as a vector in R2. Okay, very good. So why do I need this? Therefore this t is called an argument of the, I'm assuming is that it is not a complex non-zero number, because I want to write z by mod z, right? T is an argument of the complex number. Z. Okay. So the question is, can I choose unique? Okay. So now let's look at for C star. Okay, 2 or I am looking for a thing. Okay, let us call it theta of z. Let us do it. Okay, this t is not unique. So my question is, does there exist a theta? Okay, so that z going to theta of z is continuous, and such that z is mod z into e power I theta of z. E power I theta z. What does it mean? Try to understand. Do not be intimidated by this. What it says is, can you choose argument in a continuous fashion? Right? As z goes to theta z, that is the argument of z. So what do I want? I want that assignment of argument should be continuous. I know it may not be unique, but I want to choose it uniquely. Yeah. You may think this is sounds very mysterious, but you should know this question already exists elsewhere. Okay, let us have a digression. Maybe I should go to the next page. Okay, Okay, let us look at C star. Okay, so let's start with the Z here. Okay, let us say start with an alpha here. Then I say a real number, a complex number Z is a square root of alpha if Z squared equal to alpha, right? And notice that then if Z is a square root, minus Z is also square root, right? And since this is a polynomial equation, there are already two roots, and remember Z cannot be 0 because I am saying alpha is non-zero, right? Now my question I can ask is the following: suppose on C star, to see whether I have a map so that given any alpha I want to choose, okay, let me simply denote by root of alpha. This is just an okay square root of alpha. Okay, so I know the square root exists, but the point is whether I can choose this in a continuous way. Okay, again you may have a problem with this. Let me look at another simpler question. You will see these are the things once you understand you will see. Suppose I have an R star that is non-zero reals, or let us say non-zero, sorry, positive reals. Okay, positive real, that is set of all x in R so that x is positive, right? Then I can ask whether whether there is a t in R so that t squared equal to x given any x and R plus, real answers this. There are actually two things, okay, t and plus or minus t. If t is a square root, then minus t is also a square root, right? And notice that since x is non-zero, okay, t is not 0, plus or minus t is not 0, right? Therefore, by law of trichotomy, exactly one of them is positive, right? So the question I can ask is again the same: R plus to R, give me any alpha, then I want to take square root of alpha. But which square root I will take? There are t. If t is a square root, t and t minus t both are square root. Now I want to make a unique choice. In this case, I can make a unique choice. I can simply say take the non-negative or positive square root. There is no reason why you have to take non-negative. You can also take negative square root. It doesn't matter. But it's a unique choice, right? As alpha varies for positive reals, then I will choose, for example, for 4 I will take minus 2, for 9 I will take minus 3, for 16 I will take minus 4, for 100 I will take minus 10, and so on. So that's a very unique way. And what is the importance? This map is continuous. Do you understand this question? So I can choose, therefore there exists a continuous square root function on R plus. That is, there exists from alpha going to square root of alpha, which is the unique non-negative square root, unique positive square root if you want. And this is continuous, right? Now let's go back to my C star. I have a problem. You give me a square root, okay? For example, if you give me, let's say I'm on minus 1, okay? This is my z, alpha if you want, okay? Alpha equal to minus 1, okay? Then the square root z will be plus or minus I. So which one I should choose? Remember, I is also, you made a choice. There, two square root exists, choose one, right? So if I give you something, it's not clear. Okay, are you following? Please pay attention. There is nothing like unique choice. So given any alpha in C star and suppose z squared equal to alpha, then plus or minus z, which one I should choose? So alpha going to plus z. Okay, there is no such choice, nothing like positive square root. Okay, are you following? It's like saying, if you are given hand gloves, okay, a pair of hand gloves, then I can always consistently choose, let's say, glove for the right hand, right? But if you give me a pair of socks, okay, then you want me to choose one sock. There is nothing like it's a sock for the left foot or sock for the right foot or any such thing. Do you understand? There is no choice there, right? So it's not very clear. So the question is there a way to make a continuous choice? Since it's not there, I do not know which one. That is why I say alpha going to square root alpha is a multi-valued function. Remember, in modern terminology this makes no sense because any function is single valued. Okay, so in deference to our forefathers we may call it multi-valued, but it's, in my opinion, okay, in 21st century we should not continue calling it multi-valued, but anyway we will see that. You will keep saying that. Do you follow that? Pause, review, proceed before you go. Right? Now let's go to the bottom of this problem again. So suppose alpha is in C star, okay, then I know alpha is mod alpha into e power it for some t naught, right? Okay, then therefore if I want to choose a square root, I can simply say square root of alpha. Notice that mod alpha is positive, okay, real number, non-zero real number, therefore there is a unique square root. This is no problem. So I only have to say take the square root of this, but then this is t by 2, right? You will say that, but where is the problem? Multi-valuedness comes. This t is not unique. Okay, all this t, anything with 2 and pi will also work for this. Do you follow that? Therefore non-uniqueness of this square root comes from the non-uniqueness of choice of the argument. Please pay attention. Therefore multi-valuedness Are you following? So this problem is solved. Okay, so if I want to make a single valued thing, what should I do? I should choose a continuous choice of t. That means from C star to R, I am looking for a function t which is continuous, so that for every z in C star, z is mod z into e power I theta of z. Suppose there is such a choice available, okay, then I can simply define this to be square root of mod alpha into e power I theta of alpha. That's it, because I have unique choice. Do you understand this? Suppose there is a continuous function, I would have got it. So I have made a continuous choice of square root on all of C star. Please, these are the things which are never explained. Okay, you just simply intimidated by this argument, etc. But remember this. So yeah. So this is the startling result. This is one which is never proved. Usually what there is a hand waving proof. So therefore question is, does there exist such a theta? Continuous choice of argument, namely such a theta, right? So the usual hand waving argument will be like this. Suppose I take the unit circle and start from this is 0, Okay, this is my theta t. Okay, theta of 1 is 0 and theta of I is pi by 2 and theta of minus 1 will be plus pi, and theta of this minus I will be 3 pi by 2, and when I come here, see, it will be between 3 pi by 2 and 2 pi. Therefore when I come to 1, intuitively in a continuous way, I assume to get theta of 1 will be 2 pi rather than 0, right? This is 0 go along with the t, and this t becomes this, and my pi 3 pi by 2, and from 3 it keeps increasing when I come to 2 pi. This is the intuitive hand waving argument usually textbooks will give, teachers will give. Okay, therefore intuitively we think there is no continuous choice of argument, but can one prove it rigorously? Very rarely it is done, but my book I give 2 proofs. Okay, so this is a theorem. Okay, this is a very important observation. But there exists no continuous function theta from C star to R such that Z is mod Z e power I theta of Z. That means intuitively no continuous choice of the argument. Okay, so this is now proved. Okay, I can give a proof, but I will not see, as I said, I just want to give an exposition, bird's eye view, what are the real problems rather than this. Okay, now I hope I'll come to video. So what have we learned? We have learned the multitudinous, multiple valued functions arise. Such functions arise because of very simple reason. What is the reason? The reason is there are multiple choices for the argument of a non-zero complex number, right? So as we saw in positive reals, what we could ask for is whether I can choose a continuous choice of argument on entire C star. Remember, on entire positive reals I chose. So the question is, can I do something similar in C star? Okay, then there is no, I can simply define unique square root also. Okay, what is the square root I want? Fix once and for all, fix such a size of theta. Okay, a continuous argument theta from C star to R, so that Z equal to mod Z e power I theta of Z. That's it. Okay, then I can define square root, nth root, anything I can define, because there is a unique continuous choice. Okay, I can also define logarithm. I have not talked about it. I will come to it in a minute. Okay, so we have wishful thinking will be, can I do something similar? The answer is no, it's not at all possible. Now what do you do? So now let me give a real life example. Suppose I have a disease which is incurable, okay, according to modern medicine, let us say, like diabetes, hypertension, or asthma. Some of these things modern medicine says that it's not incurable. Then what can you do? Then you learn to live with it, but on the other hand, you try to make sure it is under control. You know how to control that, be it blood pressure or blood sugar or asthmatic problem, wheezing or shortness of breath, whatever. You try to control it by means of proper medication. So you also learn how to avoid, okay, which will trigger such things, and at the same time when it goes up, how to control. You follow that? So here also we are going to do the same thing. So what we are going to do is, I want to, instead of saying I want a continuous argument on all of C star, I am putting some restriction on the subset of C star on which I can say I can find a continuous argument. Okay, I will say that in a minute. Okay, so a compromise, right? Okay, okay, ignore a half line starting from 0. You can see that is like this. You can ignore any one of the lines. I hope I may not be able to draw the line, but let us just see. Suppose this is the angle theta naught, right? So what I plan to do is remove this one. It could be anyway. It could also be maybe it is this one. Okay, that's this is angle. Okay, so you remove one of them. So since I use that, let me see u of theta naught to be set of all complex numbers set in C star, so that z by mod z is not equal to e power I theta naught. Notice that this anything here will be r into e power I theta naught. R is positive, right? So you just ignore all those things. Okay, then there exists a unique continuous argument theta from, maybe I instead of this I will call it as let us say alpha. So call it u alpha e power I alpha theta from u of alpha to r, namely theta of z actually takes in alpha to alpha plus 2 pi, or it may be alpha minus pi to alpha plus pi. That means what? That is, for every z in u alpha, z is mod z into e power I theta of z. That's it. Notice that this should be intuitively obvious. Why? By intuition we already said the trouble comes from continuity. If I complete a full circle, if I start from here, I keep on moving. Okay, when I come here, my argument becomes 2 pi rather than 0. So what we are doing is you simply avoid this. Okay, don't come back. Okay, so for any number, for any complex number, non-zero complex number, what you avoid is such a line. For example, the obvious choice may be like for this. The obvious choice may be this theta. Okay, remove this. This may be the line you remove. This is alpha equal to 0. So remove this line. Okay, then this is all. I can come back, but I never reach there. Are you following? So I have done. Okay, this has to be proved. Okay, this is the result. Okay, this is again a theorem or a fact. Okay, it can be proved. Okay, in our course we will see a proof. Okay, in my book also you will see. Okay, this is proved in my book. So what have we achieved? So we have achieved. We know that there is an incurable disease, namely non-existence of a continuous argument on the entire open set of non-zero complex numbers. Okay, but our intuition told us the problem comes when you come back and complete a circle. So one particular ray, which is called a ray, just remove half line starting from origin, and then you can find it continuous argument. So then we know how to control. Right. Next thing, okay, now let's go to the next one, which all of you will be worried about: logarithms. Yeah. So suppose I have a number in C star. Okay. I Z in C is called a logarithm of alpha if alpha is e power z. Notice that this is in tune with what you do in real analysis. Okay, if x is positive and t in r is a logarithm of x, it simply means e power t is x, right? So keep this in mind. So in view of that we define logarithm. And what happens in R? In R, the exponential function from R to R plus positive reals, this is a homeomorphism. This is a bijection, continuous bijection, and it's increasing, continuous bijection, and increasing. Therefore, its inverse exists. Call this a function f. The inverse of f exists. Okay, call it g. Then what does it mean? Okay, g composite f of x must be equal to x, or if you call it t, must be equal to t, right? Because this will be g of exponential of t is t. Okay, you say, then you call g as a logarithm. And remember, if I have an increasing function on interval, its inverse is continuous. These are all part of real analysis. I don't know whether you learned these things, because in modern real analysis people only pay attention to metric spaces, so the real number things take a back seat. Okay, if you have gone through my lectures, you know this is true statement, right? So I have a logarithm, well defined logarithm, okay, namely as inverse. So I am going to call t is a logarithm of x. Now I am going to make t equal to definition logarithm of if t power t equal to x. So in view of that, we define, given a complex number alpha, z is a logarithm of alpha if alpha is e power z. Okay, now how do I find a logarithm? Okay, so alpha is in C star. Notice that again I can write alpha equal to mod alpha into e power I t for some t in r, right? And since the exponential of z plus w is exponential of z into exponential w, you can see logarithm of zw must be equal to logarithm of z plus logarithm of w, if such a logarithm exists. Are you following? Yeah. Suppose alpha is e power z, beta is e power w, then what is alpha beta? E power z into e to w, but it is e power z plus w. Therefore z is a logarithm of alpha, w is a logarithm of beta, then z plus w must be logarithm of alpha times beta. Do you understand? Therefore intuitively logarithm of alpha should be logarithm of mod alpha and logarithm of e power I t. Okay, this logarithm is not known. This I know, since mod alpha, since alpha is the non-zero, mod alpha is a positive real number. Therefore, this is a natural logarithm. Let us call it, as Americans would say, mod alpha. This is for natural logarithm. Natural logarithm in real number analysis. Okay, this I can simply define it, right? Therefore, if I exponentiate this, exponential of ln of mod alpha plus it will be e power ln of mod alpha into e power it, that will be mod alpha into e power it. So I seem to have got it, right? Now why? But it clearly shows why mod log alpha is multivalued. Why? See, here there is no problem. See, because I have a unique way of defining logarithm of a positive real number, namely take the natural logarithm. That's done. Therefore there is a natural choice. So here the problem is I have to take logarithm u power it. Obvious choice will be take it itself. But then we know this t is not unique. Do you follow that? T is not unique. T plus 2 and pi will also do that. Okay, therefore logarithm is not unique. Therefore I could have taken it to be mod alpha plus, yeah, so sorry, logarithm of alpha to be logarithm of, that is natural logarithm of alpha plus mod alpha plus t plus 2 pi n. You understand that? For any natural number n. So this is where the multitudinous comes. Now how, again as I said, what I want is I want a unique way of doing. So what is the natural thing I should ask for? Natural question to ask for is there a continuous choice of log on C star? What does that mean? Let me say call it f, just to say I want a function f from C star to C continuous, so that for every z in C star, z is e power f of z. Then f will be continuous logarithm. So from our knowledge about argument, we know there exists no continuous argument on C star. Therefore what should I expect? Yeah, I should expect there exists no continuous logarithm on C star. In fact, it's an infinite leap. Okay, so what is the next best result I can hope for? You know that. So you take u alpha where one half line is removed from C star, then on that I have continuous argument, and hence I have also a continuous logarithm. So I can define continuous logarithm. And very interesting thing, this is a non-trivial result which is very rarely proved in books, is if I have, let me just go back to screen share. With this I will stop. Okay, suppose u is an open set in C star if you want, and f from u to C is a continuous logarithm. That means for every z in u, z is e power f of z. Okay, then f is holomorphic. So in particular I know that if I choose u to be an open set in u alpha, this will happen, and I can also choose u to be a convex set in C star, convex open set, then also I can find continuous logarithm. But the interesting result I said is such a continuous logarithm is in fact holomorphic. Okay, it is holomorphic. What does it mean? If z is e power f z, f is continuous, from this I can show f dash exists. And what do you think f dash should be? Remember, z going to f of z, that going to e power f of z, this is z. Therefore by using chain rule, you know what it should be. You can find this must be 1 by z, and we have this. Okay, as I said, none of these things you might have seen in a standard course in complex analysis. Yeah, but this is proved in my book also. And the last result, uh, I proved in my book using the so-called open mapping theorem and inverse function theorem. Okay, but one can also prove it directly. In the course, perhaps I will indicate a direct proof for this result. Okay, please do not be intimidated, because none of these things would have been taught or you would have learned in thoroughly. So please go through these things. Okay, and now you have nailed down the problem where the multivaluedness of functions in complex analysis arise. That is because of lack of continuous argument. So what do? You restrict your domain, and where you can define continuous argument, and hence a continuous logarithm, and hence it's a holomorphic logarithm automatically. Right? We will come to it in the next lecture. So all these things can be done, but as I said, my main idea is to pinpoint the troublemaker for multivaluedness in complex analysis. If you have learned that, that's good enough. Don't worry. We will see all these things with rigor as we go along. Yeah, we will meet again.